You want to do it like this? Yeah, sure. Okay, hello everybody. I am Åke from Sweden. I'm here to present our solution to problem number 7, half-life sparkers. The problem description reads: sparks caused by an angle grinder tend to fly over a certain distance and then to split into several smaller sparks. What causes them to split? What's the condition for a split to occur? What influences the distance before the split? What will be the distance distribution of the sparks to fly? So my interpretation of this is to explain qualitatively why the spark split, then find a quantitative criterion for splitting, devise a method for detecting individual sparks, and then to study the distance distribution. Now, what is a spark? A spark is a tiny piece of metal that has been sent off by the grinder from the workpiece and is traveling through the air. And as we see here in the image, which looks better on another projector, they light up, and I have zoomed in here, you can see they explode and they split into multiple parts. And why did this happen? Well, this is a known problem. MC Shaw writes, ships living in grinding weir are at relatively low temperature and essentially invisible for several centimeters. As these ships pass through the air, they oxidize and the exothermal reaction energy quickly brings them to the point of incandescence and shortly thereafter they explode. And it means that they're invisible for several centimeters. We verified this by filming near grinding wheels in the appendix. Now, starting off with the modeling process, imagine you take a raw iron ship passing through the air. As it comes into contact with the oxygen, it forms an oxide layer, and for iron this is porous. And we get reaction heat of the exothermal reaction, and we get cooling from the blackbody radiation. And if it's porous, then it can keep growing due to the oxidation. And as this expands, because of the molar volume expansion, we get compressive forces in the angular direction. And to satisfy Newton's second law, we need tensile forces in the radial direction. But when the core melts, we can no longer have these forces, and then we would expect these parts to no longer remain at rest. So that's our explanation. So we need an exothermal reaction to make this able to happen, and it helps if the activation energy is low. The reaction must also be able to continue. Some metals form a protective layer of oxide when they oxide, and then the reaction stops. Some other important parameters are the volume expansion ratio when oxidizing, the melting point of the metal and the oxide, and alloying changes a wide variety of parameters. Some examples here: iron, splitting occurs regularly. Aluminum, you get no splitting, partly because of the high activation energy, but mostly because of the protective oxide film that stops any further reaction, so it can't heat up enough. Tungsten has very limited splitting due to the high melting point, and titanium is somewhere in between iron and tungsten. And we tested, and here you see different patterns. These are all iron and steel alloys. So by changing the alloy, I change chemical energies, and the problem is widely different. So I have to specify here. And also, we tested some different materials. Like here we have wrought iron. You see, this is long time exposure. It splits into two, into two, into two. It always splits into 2 pieces. And here we have steel, which splits into 10 pieces at once. So it's a wide variety of phenomena. So we choose to work with medium carbon steel for simplicity. And the enthalpy is very high. This is very high for a reaction. And this is a low activation energy. So there should be a lot of sparks from this material. Now, for the grinding, I have to explain how grinding works. When grinding wheels are made, you take the circular disc and you apply a glue called bond. And then on top of it, you put grains which act like teeth. And this is done randomly. And then, when the grinder attacks the metal, these teeth touch the metal, and the chips that are sent out are proportional to the length between 2 teeth. And so we model this mathematically, very simplified. We say that all possible placement of the grains onto the disc are uniformly probable. We say that the grain sense distribution is uniform up to a mesh limit. And I have good reasons for saying this, it's in the appendix. All grains have the same depth. That's just to make the math simpler. Oops. And our grinding model is that we get 1 chip per kinematic engagement surface. So these are the teeth, and the chip size is about the same as the kinematic distance, which is the distance between 2 teeth. Now we did a mathematical simulation of this in MATLAB, and the results are curves like this. So they have a peak. They are based upon the characteristics from the grinding wheel we used. They have a peak, and then they have an exponential tail. And there is an unknown parameter here called a fill. When you purchase your disk, then the fill is around 8%, and then it decreases with wear. And we can verify that, yes, these are the particles we find. This is the same imagery. So that theory seems to be about right. Now for the oxygen diffusion around the particle, we have a fixed second law to govern the oxygen diffusion. We have a diffusion term for the random motion of air, and we have a convection term for the mean velocity coming against the particle. And we solve this equation in an inverted ball geometry, so everything except the ball of radius r. And if we non-dimensionalize this, measure length in terms of the radius and such, then we get this dimensionless number, which compares the strength of the convective spread and the diffusive spread. And here are some numerical solutions. We are way over here, with y more than equal to 20. So what happens is that the particle traces out the cylinder behind it, and it interacts with all of those particles. So how much oxygen collides with the ship? Well, it's the area times the velocity times the density, and then it's calculated. How much heat per collision? Well, it takes 2 oxygen per reaction, so we get half the enthalpy per reaction. And how much heat is required to melt the ship? Well, first you have to heat it up to the melting point, and then you have to pay the heating latent for all of the particles. If you put this all together, we get this useful dimensionless number that's x is about 2000, and the time of the explosion is this number times r divided by v. This is the radius, this is the velocity, and the typical traverse length is this number times the radius of the particle. And we see that experimentally this holds pretty well. Oops. Now for the experimental setup. We put our grinder onto the beam, onto the bench, onto the scale, so we can measure the force, and then we use this screen. The screen is useful for limiting the flow. Without it, we get too many particles, we can't distinguish them. With it, we get much fewer, and we are able to distinguish between them. So say you have this kind of image. Now I will skip past a bit here, but what we did is that we devised an algorithm that finds the particle by using 2D hysteresis. I can explain this in more detail later. And then we constructed an ellipse and took out the principal axis of this surrounding, and then we compare the end point and the front point. Do they lie on the main principal line? If they do, then we detect it as a regular heated spark that's not exploding. But if they're lying not like that, if this is offset, then we paint it red and take it as a spark. Now we need a threshold for that, and to choose a threshold we supervise 700 events by human eye, and then we choose the concept that best fits with what the human thinks is good. So in the end our accuracy is about 80–90%. Now the force dependency is actually very slight. We have almost no change in the average distance traveled when we vary the force more than an order of magnitude. However, we do have a great change in frequency, and by frequency I mean the number of sparks that is emitted per time unit. So we get more sparks, but not faster sparks. Now, for the distance distribution, this is how it looks. It has a peak and an exponential tail. You might think it's very similar to the size of particles, and that's no coincidence. I'll get to this later. In fact, this is predicted to be the size of the particle times 2000. So if you multiply with 2000, and instead of having the probability, have the cumulative probability, then we can compare the experimental data with the model, and we see, well, it has all the right trends, but it's not quite there. So one way we could do this better is to compensate for the fact that we don't actually see the first 10 centimeters or so of the sparks, because we have our grinder, and then there's 10 centimeters to the screen, and then from the screen we start measuring. So if you adjust this sideways, add another coefficient, another fitting parameter, then we get a much better fit, and we see that the experimental data agrees with the model. Now, I have to cut something out here, but we saw here that the grinding model fits the data cumulative distribution overall. Also, in the appendix, if I try aligning the peaks of the two distributions, then I get that the best fill level is 50%. And if I try to align such that the exponential tails decrease equally slowly or quickly, then I get that 55% is the best fitting parameter for the fill. So to summarize here, the fill was an unknown parameter, and I tried fitting it with 3 different methods, and the fact that I get these all the same is a pretty good mark that the theory is at least self-consistent. So back to the problem composition. Question mark, question mark, question mark, question mark. I will answer the following questions. What causes them to split? Well, it's the melting of the core that causes the compressive forces here to send them out. What's condition? Well, you need an higher exosomal oxidation, you need low activation energy, and you need to have, it helps to have a low melting point. What's the distance for the split? It's the ship size, and here are my results. I would like to acknowledge the Happy Peter Shining Stefan Gustafsson. Thank you for listening.
Okay, first of all, thank you a lot for this nice presentation. We think that there were many positive aspects. For example, that you really considered the whole problem from many different sides of views. So you considered it from the quantitative analysis, you also had a qualitative explanation, you developed a theory, and as well you had different simulations, so it was quite accurate. Especially what was accurate was your way to analyze your data, so that you analyze your data sets by a good MATLAB program and not only like visually regarding at the pictures. So we also like that you used and explained the different materials. So in the beginning, you just tried to explain when the sparks will split and why. So you made a qualitatively analysis of this before going to the experiment. However, we think that going to the experiment was a bit too late, so we waited a bit long for the experimental setup to occur and wanted to a certain time if you only did maybe theoretical approaches. So the splitting was explained really accurately and really nice, so that everybody can understand the theory behind it and can understand why this effect occurs. So this was something we really liked. So maybe when focusing on the negative aspects, you also did not like that the parameters sometimes weren't explained really in detail. For example, we had some formulas and we missed the different variables of the formulas, so we couldn't really get a quickly overview of the different parameters depending or including in this formula. We also missed error bars in your calculation, and maybe the biggest point that we were missing was again at the end maybe a comparison between your theory, your qualitative analysis, and your experiments. Also the different experiments. For example, we found out your different materials that you used in your experiments only after asking. So it would have been nice to explain this beforehand. What's more, also on the positive side, we liked again that you just tried to explain us everything, tried to explain us a lot of things that you did, and we saw that you put lots of effort in investigating this method. But on the other hand, it was a bit too fast. What we think, there were a bit too many slides in too short time. So it was quite difficult to always get the gist and always follow your presentation. So that's why also in the technical question we asked to see some slides again. So coming to the point of discussions, we would first of all want to focus on the temperature dependencies and how did you measure them? Because we, for example, have some ideas of measuring them dependent on the color, for example. Also measuring the temperature within the sparkles or the sparkles differences, because maybe the temperature changes just directly after producing and after producing the sparkles and after traveling a short time. Also, we wanted to ask you, how did you analyze the stark pictures, as you explained this roughly with your algorithm, maybe going into more detail there, going a bit deeper, not staying on the superface. And also the dependency on the grading velocity, because we did not know what parameters you varied using the grade, because the grading, you didn't really tell about the grading system that you used, what factors it has, what pressure you have, what velocity you have to produce your sparkles in your theoretical approach. But finally, maybe to end my speech, it was really good that at the end you summarized all of the things you analyzed, all the things you did in regards to the task, so that you just again went back to the task, said, okay, what was asked in the task and what did I find out? That was something we really liked, and we're really looking forward to the discussion now. Thank you.
Thank you very much. Now you have 5 minutes of discussion.
So I have two primary rebuttals before we move on to these points of discussion. You mentioned that I didn't say anything about the specifics of the grinder, which is entirely correct. I have so much to present that I have to shorten it up. It's in the appendix.
Yes, so that's why we wanted
all the
to go
there.
there.
I can show it if you want to, but I don't think it would add anything to the discussion. But the only number you want to keep in mind is 8,000 to 10,000 RPM. That's the important number.
So, but you don't think that the parameter of the grinder is so important to?
Well, certainly, yes. The velocity is has an importance, and also the fill. I would say the grinding wheel has a much bigger impact.
Okay.
The second rebuttal was during you said that there was lacking a conclusive.
Yeah, but just maybe we're looking on the parameters, focusing more. What then do you think is the most important parameters? You said that the surface of this grinder, but what else?
So the field is really important, but I already told you that. That's how many teeth are left in the wheel.
Yes, you explained this really accurately with the teeth, but how can we say it in the theory? Where can we see the influence of the teeth in your theory? Can you maybe relate to it?
Yes, I can actually.
Okay, yes, it would be interesting.
Maybe I rushed through this if I put my...
because I think it's quite interesting. You explained this influence of the teeth, but what is...
So let me put it like this: the wheel has a constant circumference, and as we increase the number of oh, this doesn't look quite right. Can I at least flip? No, I can't. Can I?
Otherwise, you can try.
Okay, I can at least do this.
Okay.
Okay, so here, no, it was above actually. In the grinding theory, yes. Actually, I want to show the picture. Here, this picture. So I've skipped over this way too quickly. But we have a constant circumference, and when the number of teeth decrease, the average distance between two teeth increases, right? And the size of the chips, the chips are the pieces of metal that turn into sparks. The chips have a size proportional to this distance. So when we decrease the number of teeth, we get larger and larger chips.
In a proportional way, so it's a linear dependency.
Yes, for small
Okay,
lengths.
can you see this in your theoretical plottings that you did?
Yes.
So you can see a linear...
Yes, that's what's happening in here in the simulation in the results. You see that when I decrease the fill, I get larger kinematic distances, and the distribution gets skewed to larger lengths.
Okay.
So my theory actually does show this.
Okay, yeah, I agree with you. And maybe referring to this, did you measure any error bars? Or also, you at the end you said this plus minus 3%. Where do they come from? Your theory, was it dependent on your measurements or on your analysis tool? Because I think all these...
So because this simulation is very heavy to calculate, I could only do it at a discrete point.
Okay.
So I tried fill 55, fill 50, fill 55%, and then I chose the best one. And then I thought, okay, then if 55 is the best one,
like an
then we're probably in this.
Numerical.
Yes, it was a numerical simulation.
Yes, but
because this is a stochastical process, the modeling of the creation of the grinding wheel.
And you just, maybe the slide, I don't know, it was later when you had this plus minus 3% in all of your different...
Yes, so this was...
Was it dependent on the analyzing tool or on the measurements?
No, well,
the experimental setup?
No, it was dependent upon the analyzing tools. So to make it run quicker, I only ran every 5%, and then I chose the best one, and then I said plus minus 3%. So I could make this arbitrarily small if I had infinite computing power.
Okay, it depends on the computing power.
Yes.
Okay, and to your measurements only, because this, what you said, your analyzing tool, your computing power, but when you have your measurements, when you do this with different parameters, like also the dependency on your grinding, all those parameters, how accurate are those measurements? So when you pull it with just the hand or with what you, like your experimental setup?
Yes, we had well, it was partly by hand and partly, it was a human being supported by a weight, and then we applied the weight and we kept it steady, and then we only took the data from when the force was constant.
Okay, you neglected it, or you erased the...
So we did throw out some data that was bad because the human was wobbly. Okay,
and what was about your camera setup? Because...
Okay, thank you very much. Sorry I have to interrupt you.
Hello everyone, my name is Olga, I am from Team Ukraine, and now I am going to review the problem number 7, half-life sparkles. In this problem we were asked to investigate the spark splitting and find the condition of its splitting, the distance before the splitting, and distance distribution of the spark to fly. I start with the report analysis, and I would like to thank you, and I start with the strong points. We see the literature review, which was very good, and we listen the qualitative explanation based on studying oxidation reaction, with which we agree, and the reporter considered different metals, sparks produced or not, which was very good. Also we saw the experimental setup, and the reporter devised a method to classify sparks, which was already good. And also the reporter in his report obtained statistical distribution from modeling and experiment. But there were some weaknesses. The conductivity through air wasn't considered, and we didn't see the estimation why. And we missed the equation for first modeling, so it was slightly unclear. Indeed, as the opponent said, there wasn't explanation in terms mainly formally. Different metals were not considered in the experiment, unfortunately, and also different effects. For example, humidity, angular velocity wasn't considered. About the position, unfortunately, it was a very short analysis, and remarks were higher on form, but not the content. But opponent mentions the unclear presentation on the experimental setup, which is good, and brought up the question about gradient velocity. And about the discussion, the discussion was interesting enough. The opponent and reporter discussed the temperature dependence and the influence of the T's, and also the influence of kinetic distance. And here is my discussion point. I propose you to discuss impact of internal and surface inhomogeneities in the system. I propose you to discuss the thickness of the oxygen layer, how you take into account. Also, how the speed of reaction influence the effect, and random processes in the spark. Do you consider it in your modeling, and influence on the external condition? And we need to.
Okay, sorry. No. Start the 4-minute discussion between opponent.
Yes. We start the discussion.
Start from the top?
Yes, starting with the top.
Okay.
Please, first of all, reporter, and then opponent discuss this question.
So geometry here is, it's very difficult to model the oxygen and airflow going around a complexly shaped particle. What we can do is solve it for a sphere and then analyze what would happen if we change it from a sphere. So what I did was that I analyzed it from a sphere or a ball, and a ball is known for having the highest amount of volume per area, if you put an exponent such that it becomes dimensionless. So if we would make this like a pancake or a noodle or something completely different, then the area to volume ratio, and by that I mean the area to the power of 1.5 divided to volume, this would increase, and that would make it split faster.
Okay, so what conditions do you have maybe exactly related to this? Because you explained, for example, some metals, they don't work, it doesn't work. But what other conditions do you have? So for example, the shape, is there a special shape that it needs that it really happens? So what's that?
No, any shape can split if it can split.
Okay, and I think we move to the thickness of the oxygen layer. You didn't. Do you agree that we are no need in thickness of the oxygen layer in a reporter?
Because of his approximation, that
Yes.
he approximated it being infinitively small. Mm-hmm. I think that you can do it due to the method that he used, because of course you can't take all of the different parameters into account. I think it would have a slight impact as well,
But then
because
the geometry becomes much more difficult.
of course, yes, that's what I mean. I see
and
that
then
you
it
have to approximate it,
shrinks.
but what I mean
Okay.
is that of course it has an influence that might be neglectable due to to the aims that you have.
Okay.
So what I
think
can do is
I-
to take the sphere model and then have a spherical symmetric layer.
I think your opinion is clear, and let's discuss.
Sorry, but maybe I wanted to come back to this because due to the oxide layer, I think it has an the impact, especially on the radiation. And this, for example, you didn't take into account, or you didn't mention the radiation if you approximated it as you did something about this, or because I think that the oxide layer, it's an exothermal reaction, of course. If it's thicker, then you also have a higher radiation, what influences the whole
So
system.
I think bringing up radiation is a good point, because common sense should say, why isn't blackbody radiation relevant? It's over 1,000 Kelvin. And the answer to that is that, well, the blackbody radiation is huge by everyday standards, but this reaction heating is even greater. So I did an example in my appendix where I showed that if you have around 1800 kelvins, then still the blackbody radiation is only a tenth of the heating from the exothermal reaction.
Okay, okay. I think we move to the this question about influence of the external condition. For example, humidity, how it influence, and first of all, reporters and
I would say as long as humidity is reasonable and air temperature, I would say they are much more down on the list than the other parameters.
And do you agree with this point?
I actually agree. I think there are other different other parameters that are quite more. But of course, when you have a really, really high relative humidity, then the whole effect would not occur because the sparkles would die before they can split. This might be a parameter, but this might not be a parameter that influences the whole system gradually, but it might be a threshold. So like a threshold, and at this point, it won't work at all.
Mm-hmm.
That's what I think.
Okay, I think it's time to move to the general discussion. First of all, we start with the reporters team. Do you want to add some points to the discussion? Okay.
Okay,
maybe opponent team.
maybe then I can also ask a question to this.
Yes, I think the opponent has
I
lots of
suppose
questions.
you have to ask first of all the teams, and then do you want or not?
Yeah, I have a question.
Okay.
So which camera have you used, or did you take the angle into account also from the sparkles, you know? And you measured it?
So yes, I did use polar coordinates to compensate that when I have my screen here and the sparks come out like this, and my camera is over here, then you're right that it's this angle should not be neglected. And I did take this into consideration just by using polar geometry.
And how did you, when you took the photo, I think it was two-dimensional, how did you take into account the three-dimensional split, for example?
Well, the motion,
as they are not only splitting like this, but
after
also
the
like this.
screen, the motion is only in one dimension pretty much.
The motion, but the split, I don't think. I think they are also slightly
so,
split
okay,
in this
actually,
one.
that's a good point.
Okay,
So each split might actually have more particles that are going perpendicular to a camera that we did not see. But that's not really important because I did not analyze the number of sparks being split. I only analyzed when they split.
Okay, and they were
I see your point of view is clear, and let's move to the reviewer team's question.
Yes, I have the following question. We obviously understand that the distance and the exudation direction highly depend on the speed with which the spark is moving. Like if the spark was stationary, the oxidation direction would be much slower.
No,
So,
this can be experimentally disproved.
and
If you, may I?
Yeah.
Okay, so there is a particle called iron oxalate, which is one iron and 2 carbon dioxide, and you can prepare this as a salt, and if you put it in vacuum and heat it above 60 degrees Celsius, then the bonds to the carbon dioxide will separate, and you will have pure iron, and then when you expose this flask to the air, then it explodes in contact with oxygen. So iron is highly reactive with oxygen in room temperature. The reason your pants doesn't burst into flames is because they have a protective layer, and if you were to cut them open, then it would be such a huge volume to area ratio that it wouldn't be significant
But
heating.
at the same time, the velocity, of course, has an influence. Because, for example, did you do the experiments also with stationary, you know, these kind of candles that sparkle, the sparkles? Maybe you know them, just like small, tiny splits. They sparkle when you just only light them. And there you don't have any velocity traveling, and I think the sparkles are differently. That's
But
related
isn't
to
this
his...
a completely different issue?
No, he talked about the velocity influences, right?
Yes,
The
but
yes,
how the oxidation
and-
direction influences like the velocity, the flow of oxygen to the spark increases the oxidation.
So let me be clear.
Yes.
The velocity decreases the time, but it also it keeps the length constant, as you saw in my formula. The typical time until explosion was x times the radius divided by the velocity, but the distance traveled, which is what we're investigating in this problem, was simply x times the radius of the particle.
Okay.
Oh, okay, and I think we should give the words to the reporter team if you need. Okay, and opponent team, do you want to ask something?
Can you give us a approximate temperature and speed that were involved in the process?
So the temperature, because it melts, it gets up to the melting point of iron, about 1500 Celsius, and we verify this by taking the color of the particles. As you know, you can, if you have the color of something, you know its temperature due to the blackbody radiator.
Yes, that's what I suggested in my
So that's the temperature. The velocity is actually rather constant. It depends on, it was about 2 meters per second. And it depends on the grinder, it depends more on the grinding than the grinder itself and the force applied. I have some references studying the velocity as a function of different...
Okay,
And
I think that we need to move to the last question from the
maybe
viewer
one
team.
just to this
We
one.
have already smaller time.
Okay, I have a following question. If we study one spark which split it and then moved on and split it for the second time, how is it likely, does the distance change of by
So
this second
in our
spark
measurements,
or-
we only used photos that was separated by enough time such that we would not measure a spark twice.
And you didn't study in the modeling and...
No, after it has exploded once, we don't care.
Okay.
So they only investigated the first. Okay.
Yes, I think the time is over. Thank you, and it's time for concluding remarks from the reporter.
So, in conclusion, I would like to thank the opponent for discussing with me and the reviewer for leading the discussion. I will say I think the reviewer was a bit of a second opponent in this case, only asking questions towards me and why I did stuff. As for my work, I brought up the problem description, I took my interpretation, and I solved this problem, and in the end, I summarized. So the main mechanism here has to do with the exothermal oxidation of iron. And that's what makes this happen in general. Thank you.
Okay, thank you. It's time to jury questions.
Yeah. You have 6 minutes for jury questions. I remind you that your grades should not be based strictly on these questions, but on the fight we just saw.
I think Cher should direct the questions.
Please.
Thank you. You were showing some images of the particles in your presentation.
Yes.
These images were made by you, or did you just get them from the internet?
It was made by my
By your
assistant.
team, of course.
Yes, by it was not from internet. Actually, I skipped over this, but in the end, I had acknowledgements, and these pictures were made by the help of Stefan Gustafsson at Chalmers. So I went to him, I said, here are my samples, could you take photos? And then we sat together, and he used the same, and I said what he should capture.
Okay, so did because you skipped this slide immediately, so what, did you take pictures of the particles at different stages of their life?
Yes, and this is a...
And did you make any conclusions based on these pictures?
Yes, you bring up a very interesting point, because could somebody please plug this in for me? Yeah, Swedish team go. Let me draw the pictures meanwhile. So there are two main types of particles. One type is completely spherical. It's almost scary how perfect it is. And others looks kind of like macaroni, something like this. And what I believe is happening is that when you have the teeth going into the material, they produce macaroni shapes like this. But after they have heated and melted, then the surface tension makes them fall into balls. So I believe that this is before melting and this is after melting. And I can show you images of this.
I think only these images are quite okay. So, if you take the particles right at the edge of the metal, you are processing, right, by the wheel. you will have macaroni,
Mhm.
and sometime at a certain distance you will have more ball-shaped particles. Is it?
Yes.
And then your model applies to these ball-shaped ones.
Ah.
They have to, something has to happen before they split,
Mhm.
right? Is it correct?
Yes, so this is how they look after they have split and molten. So I should say there's some confusion here about when I show my spherical model, I assume these to be spherical as
Ah,
well,
okay.
which could be confusing.
Mm-hmm.
Okay, sure. Yes.
Yes, so it's a question for you, but also for the other. What is the main cooling process after the sparkle are created?
So before the explosion, but after the grinding. Yes, then the,
You observe sparkles,
yes,
and so what happens then?
after the explosion.
Yes.
Yes. Okay.
Or
So
not.
so they cool off because this oxide layer progressively builds up, and they become more and more filled with oxide, and then you get this protective film that makes the oxygen unable to reach the iron core, and then they can't react anymore, and then they lose heat mainly to the blackbody radiation.
I assume that also when they just, you have melted sparkles like these shapes, and after they sparkle and split into, they just don't continue to be the melting sparkles anymore, but they just continue to glow. Now that's
So if
the
they're
change
big
that
enough,
I
they can
see.
do multiple splits.
Actually, related to this slide here, you calculate how much oxygen collides with the chip
Yes.
or with the sphere.
Yes.
And you're assuming, if I understand this correctly, that all the oxygen that you calculate in this way reacts. There's a 100% reaction probability.
Yes, I do, and that needs to be motivated. I understand.
And you also think that the right speed to put in here is the velocity of the particle and not, say,
The air
the mean
motion.
velocity of
Mhm.
oxygen and air?
That's a very good observation, because usually the velocity of the particles in the air are much faster than particles. You would expect them to be relevant. However, what happens, first I look at the energies in iron, and since iron oxidation has such a low reaction energy, it always reacts. It's not very common, but it happens. And when you have this situation, when the iron reacts with all the oxygen, what happens here is that the particle that's here, it kind of gets this protective layer of air that has very low oxygen density. So in the stationary case, it is actually the velocity of the particle that's relevant. However, this is dependent upon the dimensionless number. If we had been here, then I should have used the mean velocity of air. But since I'm over here, I should use the velocity of the big particle.
So these two things are actually connected. This is a good assumption
Yes.
because you have units. of
Precisely.
reaction. Yeah.
So I look at this slide.
Do you have any other
I
questions
say-
from the jury?
I say, because y is so great, I can use this approximation.
Yeah, sure. I get it.
If I may, how in your model you corrected from the spring effect? Can you tell me a little bit
Screen
more?
effect.
Yes, you said the model that fit the experimental data
Ah.
unless you make some correction.
Yes.
You didn't say much about it.
No, my bad. So so here's the grinding wheel, and we get sparkles that are emitted, and then we have a screen. So what we observe is only this part, but the theory starts from here. So for the theory, x equals 0 is over here. However, for the camera, x equals 0 is over here. So what I did was that I
Very
shifted
fast.
the position
Very
to
fast.
compensate for this.
So it was just a general shift from
Yeah,
all the
I just
data.
shifted it to 10 or 7 centimeters, something.
Okay, thank you very much.
Now the jury